Hi, Ashley. We're back to the dreaded problem N. I wasn't happy with my solution from yesterday on that other video. So I thought of a more systematic approach. Maybe this will be helpful, maybe it won't, but at least you'll see that there is a real systematic approach that's follows a series of repeated steps. Okay, so we're starting with the function here. And again, I got rid of f of x and I'm using y, because then we can think in terms of dy dx, dy d this, dy d that. And so instead of starting with a big picture, let's focus in on some of the simplest component functions of this complex composite function. So the first one that catches my eye is this x squared, because I know we can differentiate that. So I've got a let column here for substitution. So we're going to let p equal x squared. And a then column, we can take the derivatives. So dp dx equals 2x. So we're off. That's pretty simple. Another simple function, something we can differentiate, is this right here, 1 plus 4x. Let q equal 1 plus 4x. Then dq dx equals 4. That's easy. Okay. Now, again, so we don't lose track of where we are, what we're doing. Let's go back and make some substitutions over here on the left. So now y simply equals p plus q to the 1/2 all to the 1/2 power. And now we see another simple function that we can differentiate. So we're going to let r equal q to the 1/2. And we can start to differentiate that. So dr dq equals 1/2 q to the negative 1/2. But wait a minute, eventually we're going to want to know what dr dx is. So let's do that. So dr dx equals, dr dq times dq dx. Well, let's just go along and fill that in. So it's dr dx equals 1/2 q to the negative 1/2. That's the r dq part. And what's dq dx? Well, that's up here. It's just 4. So simplifying that, we get 4 times 1/2. That's 2 times q to the negative 1/2. But what's q? It's 1 plus 4x to the negative, let's see, 1 plus 4x. But yeah, we have to take that to the negative 1/2 power. So there's dr dx. So we've got dq dx, we've got dr dx. We're on our way. Next step, go back over here and make some further substitutions. We've got y equals p plus r to the 1/2. Okay, so we're going to let, here's something looks pretty simple. Let's let s equal p plus r. Let me sort of draw a line like that. Okay, but this is different. This s is not a composite function of p and r. It's simply the addition of two functions, both of which are functions of x. So this is a moment to pause, because we're not dealing with composite functions. Let's fill in the gaps. What we're going to want is ds dx. Well, that's just dp dx plus dr dx. But we've got those already. That's just equals 2x. That's dp dx from up here. And dr dx we got right here. So dr dx is, so it's plus 2 times 1 plus 4x to the negative 1/2. Okay. Now we go back to our original problem. But you can see what the pattern is. On the right-hand side, we're trying to get all of our terms eventually, when we're talking about the derivatives, into functions of x, so that the derivative is expressed solely in terms of x. So let's go back to the right. We got y equals p plus r to the 1/2. Well, that's s to the 1/2. Okay, that's easy. So now we're ready over here. We can now differentiate. We can say dy ds equals 1/2 times s to the negative 1/2. And I'm not going to substitute for s right now because it's getting back to a complex expression. So let's just use s for now as a placeholder. But if we want to know what dy dx is, which is the ultimate question, it's easy to say that that's going to equal dy ds times ds dx. And we know what these are. This is dy ds is 1/2 s to the negative 1/2. And ds dx, well, that's right over here. So that's going to be 2x plus 2 to the 1 plus 4x to the negative 1/2. And we're basically done, although we'd have to go back and substitute for s, or we could just say where s equals, and you can go back through these steps up here, boom, 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 boom. Or you can just realize that s is this expression here. And so it's s equals x squared plus 1 plus 4x to the 1/2. Done.